Okay, so in the last previous discussion, we arrived at this important result that tau yx was equal to tau xy, and then we had also said, without actually giving an explicit proof, that even in three-dimensional cases, the shear components of the stress would be symmetric in the sense tau zy will be equal to tau yz and tau xy will be equal to tau yx and tau xz will be equal to tau zx. So that was something which we arrived by taking a sigma m, the moments about the center of this solid, as 0. Now let's consider this figure 4.11. It says something very similar, very sort of important, and that is that if tau xy was a negative number, then tau yx would also have to be a negative number and obviously of the same magnitude. Okay, thus the two shear stress components associated with the xy set of axes must be both be positive or both be negative. Okay, you cannot have them of different signs. So this particular figure are shown in possibilities are shown in figure 4.11, where because of 4.12 we use the same subscript sequence to identify the shear stress component on both the x and the y faces. Okay, so you have a positive tau xy, you have a negative tau xy. That's how we have gone about it. Okay, so this is something which makes our life very easy. Now we don't have to worry about the face and things like that, and the symbols speak for themselves. Okay, now let's go back to equation 4.9, which was the summation. So 4.9 was summation of fx equal to 0, and 4.10 was summation of fy was equal to 0. So if you go to 4.9 and 4.10, you can find using 4.12. So once you use this in 4.9 and 4.10, basically replace tau yx with the tau xy, and then you should arrive at this equation, these equations, both in the x and the y direction. And tau xy So this is 4.13, and you have essentially done by using this 4.12 in this one. Okay, so these specify the relations which must exist between the partial derivatives of the stress components on perpendicular faces at a point in order to satisfy sigma f equal to 0. So remember, there was only sigma x tau xy, and this now also has become tau xy because of the symmetry. This is so these three stress components satisfy these two relations. Okay, and this has been arrived by taking a sigma f equal to 0. Okay, now you want to summarize this, and then you say that the equilibrium imposes certain conditions, which is 4.12 and 4.13 on the stress components in plane stress conditions, and you want to sort of extend it to that 3 dimensions. We don't show that derivation right now, but in some problem or elsewhere you will be able to do that using the same idea. So this equation, for example, this equations can be written as dou sigma 1 1 by dou x1 plus dou sigma 2 1 by dou x2 plus dou sigma 3 1 by dou x3 is equal to 0. In the shorthand notation, this is written by so in 2 dimensions you have two equations like sigma x fx equal to 0, sigma fy equal to 0. In 3 dimensions you will have three such equilibrium equations. So that would go from I equal to 1 to 3, and this shows that there is a summation over I. Okay, so this symbol you must have seen somewhere. Again, in this course we will not be using the indicial notations, but just so that you know, we have to put it out there. Okay, so there is a sign convention which tells you that the repeated index which you have, so over here the repeated index is I, so it is automatically implicit that the summation is over I, which is the repeated index. So this can also be written as, okay, again as I have said before, I mean this symbol and notations are useful for some advanced concepts of elasticity, which in this course we don't want to get into that. It does take away the visualization out of your thinking about solid mechanics. So that's why we are sticking to the XYZ notation. Anyways, so let me just cut this part out. Now remember earlier we had mentioned about a very important part of stress tensor. We had said that Tn was a stress vector, okay, which was acting at a point, and then we had given out these 1 2 3 1 2 3 1 2 3 three sort of 9 components of stress tensor, where each row represent the components of the stress vector along the ith direction or in the x-axis direction. This represents the components of the stress tensor when calculated along the y direction or the j direction, and this would be along the z or the k direction. Okay, so what we had left out at that time, what is the relationship between this arbitrary, okay, arbitrarily aligned tensor stress vector and these specific three special directions? Okay, we know what those three special directions are. So the stress tensor defined along stress vector defined along these three special directions, and the arbitrary defined stress vector. We want to now find the relationship between these components. We had left it out before for section 4.5, and that has come now. So let's see how we can do that. Just move up. Okay. Okay. So what we say is this. So in the previous sections, we have determined the conditions which equilibrium imposes upon the stress components on perpendicular faces at points in a stress body. Remember, in the previous case, the stress components which we had written for plane stress were actually only about these three specially defined directions. Okay, and the n was only one of these three cases. Okay, so they were special cases, but now we are dealing with the stress vector and how it's related to these three special directions. So you want to find how to express these components in terms of this, and let's start with that, and we'll see how this is in fact one of the most important results in solid mechanics in this whole subject, which begins over here. So let's assume that we know the values of the stress component sigma x, sigma y and tau xy at some point in a body subjected to plane stress. Okay, so we are, for the sake of simplicity, not considering a three-dimensional case. Okay, we'll just take a plane stress condition and we will assume that uh, we know the component sigma x, sigma y and tau xy at a point on the body subjected to plane stress. So that means that, simple language, if you have this two-dimensional body at any point, you know the value of sigma x, sigma y, tau xy, the numerical value of this. Now, what would be the stress tensor at this point, stress vector at this point? Okay, so T n this point, what would be this in terms of these three things which you already know of? Remember, these are specially aligned. Okay, so let's look at figure 4.12, 4.12. Does the equilibrium uniquely determine the components, these components of this vector? Okay, if you have equilibrium, can you find this, or in the sense, can you find these two circled components? Because if you find them, then you have this vector. Okay, that is what we want to investigate now. Obviously, in terms of sigma x, sigma y, tau xy, and clearly theta, which is the angle this normal has with respect to the x-axis. Okay, so let's start with that and look at figure 4.13. So the point O is again, we have considered a small wedge. Okay, we have a small wedge which we have cut out from there, from this figure, and the point O should be, okay, the point O is over here. For a sufficiently small wedge, okay, the smallness has to be taken care of, just like this was small. Okay, similarly this wedge is also small. For a sufficiently small wedge, we can consider the stress components to be uniform over each face. So the equilibrium requirements sigma m equal to 0 and sigma f equal to 0 can be expressed. So let's see, for this small wedge, we want to apply sigma m z equal to 0. That would be, let's start with tau xy multiplied by delta z. So we want to just take care of this one first. Okay, tau xy, that would be multiplied by delta z. Okay, and what would be the mp? Seems to be okay. mp is this length between m and p. That gives the area over there. Okay, area of that rectangle, and the lever arm would be np by 2. Okay, so this is not a vector, it's just a bar which shows the segment. Okay, that's why there's no arrow on this. Now then, this is the first direction. Look at the other component, then you again have a tau xy, but the sense of this will be in the opposite direction. That's why you have a negative sign. Okay, and then this is of delta z and np. The lever arm this time is mp by 2. Okay, so that's the moment balance for this wedge. And secondly, you will have a sigma fx, that would be in the x direction. What all do you have? Well, first thing you have is the traction vector. So what you do is you take the x component of this vector and then multiply it by the respective areas. So the traction x component, this is a scalar. Okay, tx is a scalar. So then you want to multiply it by a suitable area, and that area should be delta z multiplied by mn. Okay, it's this inclined plane which you have, and the lever arm this time, oh, there's no lever because it's not a moment, so it's just a force. Okay, and okay, fine. So that's the case. One important thing, I mean, in the previous this one, you didn't take the moment about this because of this force. The reason was that force was passing through O, which is over here at the center. So O point is over here. So this O is on this inclined plane. Okay, this is on the inclined plane. So the point O lies on the inclined plane and passes through Tn, hence you didn't consider that moment. Anyways, so for this is sigma fx. Now in the x direction, you should have a minus sigma x, this one. You again do this delta z into mn cos theta. What this does is, this mn cos theta is essentially the projection which you would have on this plane. Essentially you want this to be equal to mp. Okay, and similarly you should write tau xy into delta z for mn sine theta. Okay, so that's what we do. So this mn cos theta is actually equal to mp. This mn sine theta is actually equal to np. Okay, so the angles you have to take out, and okay, so essentially this is the, okay, fine. So similarly you would do a sigma fy equal to 0. Again, I am not writing, but this has to be equal to 0. So sigma fy also has to be 0. And once you do these three things, the moment equilibrium has to be satisfied by itself. So your textbook, the author in your textbook says the moment equilibrium, this equation, is satisfied identically. What does this identically satisfying mean? Okay, it means that, I mean, this just gets cancelled with itself, all the terms over here. So this is called satisfying identically. You should make a note of this language. Okay, so you don't have to specially satisfy it. It is satisfying just by cancelling each other's terms out. Okay, so you don't have to worry about that. This is an expected result since it was a satisfaction of moment equilibrium which led to the result 4.12. So this was exactly what had led to this, sorry, 4.12 over here. Okay, now coming to the other two, you have to simplify this one and this one, and you should be able to get and sorry, this is not a vector, it's a scalar. Okay, so simplifying these two conditions, you should be able to get these terms. Okay, so this 4.19 is what this equation is, and what it does is it gives us the components of the stress vector acting on an element of area whose unit normal is n. So if you have to write this vector n, what would that be? Is it okay to write it as cos theta I cap plus sine theta j cap? Okay, because it's a unit vector, so it can be written in the x component of this n vector is essentially cos theta, and y component is sine theta. So we have already done that, and this is essentially the important result which we had been waiting for. We have found out that this arbitrarily oriented traction vector can be written through these two components. So Tn will be equal to Tx of n I cap plus Ty of n j cap. Okay, this arbitrarily oriented stress vector can be written in terms of these special stress components which were arrived at after considering these special directions, only 3 in 3-dimensional case and 2 in 2-dimensional case. Okay, so this is what we have arrived at, and the language is so important over here. It says this: a knowledge of the vector components in terms of the components on coordinate faces is often required at the boundary of a thin body. So similar result will hold for a 3-dimensional case. We won't derive it now, but you will do it in one of the later sections perhaps. Okay, so it will just have some other terms plus and plus, and then you should go it. If you are getting very impatient, you can please check section 4.15. Okay, so there you have the 3-dimensional relationship between this. We don't do it in this class because actually it requires a use of indicial notations. Though mathematically that is easy, but the physical and the visual interpretation is much easier if we do it this way. Okay, so that's how we arrive at this. Now the next question which we should consider is, do the known stress components in the x and y phase determine the stress components on a face which pass through the point and whose normal x dash lies in the xy plane and makes an arbitrary angle theta with the x-axis. Look at this diagram 414. Look at the point O again, and clearly it's a thin plate. Okay, because we want the plane stress to be valid, so that you see it's thin plate, you have the external forces. Okay, now the question remains the same. You have the sigma x, sigma y, tau xy at O, at the point O. You are using this relation, you can find the traction vector Tn, stress vector at this point. Okay, using these relations, the question is this: if my plane, which can be infinite, there are infinite possibilities to be inclined, but now I am looking to find sigma x dash, sigma y dash and tau x dash y dash for a plane which has this orientation, this strip which you see. Okay, now my plane, I know that Tn can be any arbitrary shape, but now if I am looking for these stress components along a plane which is not lying along the I, J or K directions, but instead it is lying along this particular, as a normal to this particular plane, what would that value be? Okay, and that is what we will want to find. Can we find out those values? So can we find out sigma xy in terms of sigma x, sigma y, tau xy, and obviously theta. Okay, theta is shown over here. So your new coordinate system is x dash, y dash. Okay, and you want to find out these stress components in this new coordinate system now. Can we do that? That's the first question. Okay. So you want to answer that by considering the equilibrium of, again we take a small wedge of this form, okay, and the same orientations are now shown to you. X, y and z are there as they were, but now this new system is x dash and y dash, and you again proceed in the very same way with sigma fx dash equal to 0. So now you have to do all the resolutions of the forces along the x dash direction. I will do one of it for you, okay. So let's start with this. You write sigma, so sigma fx dash is equal to 0, so this dash is on the x, okay. So let's see, sigma x dash has to be multiplied by a suitable area. What would that be? Delta z multiplied by mn. Okay, that makes it easy. Now let's consider another force. So sigma x, for example, this one. What you have to do is you have to take the force first. Sigma x multiplied by the area delta z mp. Now this force is actually acting in this direction. You have to resolve it into this direction, okay, with because you have already put a minus sign, so you want the component of this force, or the projection is of this force on this dashed or dotted line, okay. That would happen how? You would have to use cos theta, okay. This is there, so this must also be a theta, so this becomes a cos theta. Now let's look at the other term. I'll just cut this out, okay. Let's look at the other term, which is sigma y, tau xy. Tau xy is over here, okay. You again use this one and multiply it by a delta z into mp again, okay. We are referring to this one, and you want, so this is the direction which you have, but you want it to be resolved in this one, okay. So this time you will have to use sine theta. Now again you repeat the same for sigma y and tau xy, and you should have a relationship, okay, which is there in your book as equation 4.21. You repeat the same analysis for sigma y dash equal to 0, and you find another such relationship. You want to now convert this 4.21, this one and this one, 4.21 and 4.22, and once you sort of do some trigonometric relationships which you have to apply, you should be able to get this. Sigma x dash is equal to sigma x cos square theta plus sigma y sine square theta plus 2 times of tau xy sine theta cos theta. Similarly, sigma y, okay, sigma tau xy, let's call tau x dash y dash will be equal to sigma y minus sigma x sine theta cos theta plus 2 times plus tau xy cos square theta minus sine square theta. I strongly recommend you to actually derive this using 4.21 and 4.22. Okay, I am skipping it because I think it is something which you can easily do, but sometimes all of us know, I mean, we surprise ourselves. Sometimes the simplest of the things are harder to do. Okay, so please do this, do not leave it without the derivations. Okay, so this is what you would get, and this 4.23 is what this equation is, and it, according to the author of your textbook, gives the answer to your question. The stress component sigma x dash and tau x dash y dash at the point O are uniquely determined by the stress by the equilibrium from the stress component sigma x, sigma y, tau xy, and the angle theta. Okay, so you said unique answer. I mean, in the sense it's unique in the sense, I mean, you will, for a given sigma x, sigma y, and tau xy and theta, you will get only one sigma x dash and one tau x tau y dash. Okay. So that is how you have found two values. Now there is one small trick left out in this play. So from this equation, you are sure that the plane stress, if you know the stress components on any two perpendicular faces, we know the stress components on all faces whose normals lie in the plane. Okay. If you want to, now what you do is this. In this diagram, 4.15, replace theta by theta plus pi by 2. Okay, you do this in the sense this theta will be theta plus pi by 2. Okay, so can you see that once at the angle lying at theta is axis lying at theta is x dash, and the one lying at theta plus pi by 2 is y dash. So doing this operation, you actually replace this x dash with y dash. So all you have to do is, you in this equation, please replace theta by theta plus pi by 2, and then this will become sigma y dash. So that it becomes equal to 4.24. Okay. So this gives you the answer that if you, and this is one of the most powerful results which you have. If you know the stress components of for all possible orientations of faces through the point of question, you say that you know the state of stress at the point. So if you know sigma x, tau xy, tau xz, sigma y, tau yx, tau yz, tau zx, tau zy, sigma z. This is the state of stress. Okay, just using this. Okay, in a three-dimensional case, we have done it for two dimensions. Just using this for a three-dimensional case, you can find the stress component for any orientation. Okay, so you had this three-dimensional piece of solid, and say you have these values, these 9 values, or essentially 6 values you have. So you can find the value of stress for any plane arbitrarily inclined. All you have to do is find this plane which you see over here, and that's it. You just have to know the orientation of the plane. So any of these planes, any of these infinite possibilities, we have shown it for one particular case over here in this derivation, but you can replace this theta by anything, right? Of the infinite values theta can take, and you can have an answer for yourself. So this is why you say it's called state of stress. If we know the stress components for all possible orientations of faces through the point in question, we say that we know the state of stress at that point. And for knowing the state of stress at that point, you need to only know this. With this, you can find all the components of stress for any possibility of orientation of the plane through which you are hypothetically cutting out at that point. Do keep in mind that now the cut is made at the point O, which is lying on this inclined plane. O is not there on this vertex. Okay, O is not there. O is on the plane. Please keep this in mind when you use this. Okay, so this brings us to this next sort of topic, which is called the Mohrs circle representation of plane stress. And we are taking plane stress again just because we can draw the diagrams nicely and interpret the results in a better way. But most of these results, I mean, you see, they will be extendable to 3 dimensions as well. Okay, For the sake of learning, we are using this 2 dimensions. Okay, so let's get this rolling. So from the previous derivation which you have, I'll just write out the equations, which is sigma x dash is equal to sigma x. I mean, you can write it like this, 4.23 and 4.24. This, sorry, it's a minus sign. So you should please verify this, okay? If there's any typo or some sort of an error, it will come out in that. Because we have grown into this course doing every derivation. The purpose was that you would now be not hesitant in trying to solve or actually verify things for yourself, so that you can be a good fact checker. Okay, so we have written this using this double angle, I mean cos 2 theta and sin 2 thetas. Okay, we have intentionally done that for a reason, 4.23 and 4.24. So please verify this. You would already know the trigonometric properties of these double angles. Okay, now please look at equation figure 4.6a. Okay, 4.6a, let me just see. Okay. So in this figure, we make a graphical representation of the first of 4.25. So we want to make a graphical representation of this figure. This is 4.25. We want to graphically do this by laying out sigma x dash along the horizontal sigma axis. So this is the horizontal sigma axis. The first term on the right of the equation for sigma x dash, this term, is represented by OC. Let's see. Okay, OC is of length sigma x plus sigma y by 2. Okay, so this checks out. Okay, and then the second term on the right is represented by the horizontal component of CB. So second term on the right, which is this term, is represented by the horizontal component of CB. So CB, if you look, is this. The angle which CB makes with this sigma axis is 2 theta, and hence CB cos 2 theta will be this little length. Okay, so that is what this part is. Okay, I'll just remove this now. Now the third term is represented by the horizontal component of BA. So BA, let's look at where BA is. Okay, this is over here. Now this, and you see the angle 2 theta is marked. Okay, so BA cos 2 theta will be this thing. Okay, but we are looking for BA sin 2 theta. Okay, since we want to move in the sigma direction, so BA sin 2 theta would be somewhere over here. Okay, so this length is over here. Okay, so what we have done is we have arrived here, then we calculated this one and then this one. So finally we have arrived at this place called A, and that is what sigma x dash is. Okay, so this is how we have graphically represented sigma x dash, and okay, the normal stress sigma x dash is thus represented by the abscissa of point A. So the abscissa of point A will be sigma x dash. Okay, now let's turn to this equation, this second equation, tau x dash y dash, and we want to graphically see this as well. Okay, so the previous construction may also be used for this purpose if we consider shear stresses to be laid out vertically. So this is tau over here, and this we are laying out vertically now. The normal stress was in this x direction, abscissa. This is the uh, ordinate, and okay, the first term on the right, let's write out over here. The first term on this is what, minus sigma x minus y by 2 sine 2 theta. Okay, this term, and the first term on the right of the equation of tau x dash y dash is represented by the vertical component of CB. Let's look at CB. Okay, so that vertical component is this one. Okay, that would make this as minus sigma x minus sigma y by 2 sine 2 theta. Okay, and I mean, you can look what CB and BA are, all these, that's why we are saying this. Okay, it's already given what CB and BA are. So anyways, so this is how we have. So first let's look at it graphically, don't look at the values first. Let's see whether you can actually arrive at this number. So the vertical component is this one, and then the other part which we have is sorry, and the second term is represented by the vertical component of BA. Okay, so you have this component of BA, which is the vertical, I'm sorry, okay, BA. Okay, this is the vertical component, and it's for tau xy cos 2 theta. Okay, so we have got that. So let's see how does this actually become these, I mean, the summation of these two terms. So tau x dash y dash can be seen as the difference between, so what you do is you have this and then there is a minus sign over here. Okay, so you cut that part out of this, which is this part, cut this out, all you are left out with this particular part. So that is what tau x dash y dash is. Okay, this one over here, because of the minus sign. So it's like you have this one as plus and then you are cutting out this minus part, so all you are left out is with this. So this is this part. Okay, so that's the downward ordinate of point A. So what we have seen until now is that the abscissa of point A is sigma x dash. We have seen that the downward ordinate of point A is tau x dash y dash, right? Okay, now in a similar manner the construction CDE. Okay, so what we have considered now is the construction CBE until now. Okay, for these two, you can use the construction CDE for representation of these two again. So use a construction CDE in the very same manner. Okay, and you should be able to get the normal stress sigma y dash, in which it will represent the abscissa of point E, and the ordinate of E should give you tau x dash y dash. Okay, so that's how you have to graphically see this derivation. One thing which I would very strongly urge you again, please do this for CDE construction. Okay, this will be the only way that you will ever understand whether you have actually understood this CBE construction well enough. Okay, this is the only way to verify this. So please don't leave it by just saying like I am doing it in this class, that similarly you will find the answer. Please do that and write the equations yourself. Okay, and point out to the respective points as you go along, what term is what. Okay, and so on. Now in this figure which we have just seen, 416a, the line ABCDE with its two right angle turns at B and D. Okay, there are two right angle turns, it's shown by this point. Okay, B and D, there are right angle turns. So this line ABCDE with its two right angle turns at B and D is completely fixed by the original set of stress components sigma x, sigma y, tau xy. Only this orientation depends on the angle theta of figure 4.15. Okay, only its orientation depends on the angle theta, which we have seen so in 4.15 over here. Okay, now because we use these equations sigma x dash from 4.15, these equations which are there. Okay, let me just, so this all was coming from equation 4.15. okay, if we permit the angle theta to change, okay, everyone can see a theta in 4.16a, you permit the theta to change, the line ABCDE would change its orientation, right? Right now you have ABCDE as you see it on your screen, but as theta changes, for example, this angle 2 theta becomes 2 theta plus 35 degrees. Okay, so all these angles will become 2 theta plus 35 degrees, and hence you would say this would rotate in a certain manner, right? This would rotate, this would move here, this would move here, and that's what they would do is they would trace out arcs. So when this 2 theta increases say by 35 degrees or 45 degrees, this makes an arc, this makes an arc. If it decreases by 45 degrees, it moves on this side, it moves on this side, and so on. So it will trace a arc like a windmill, the center of which will be at C. Okay, C will be the center of this construction of arcs which is going on by the variation of theta. And nothing is wrong over here because theta can actually take any value, right? That's the whole point of what we have just done. So that's the case. Now a particular orientation of interest is that of theta equal to 0 degrees. Okay, now please look at 4.16b. I'll just rub this part out so that there is some clarity. Okay, please look at 4.16b, and you have theta is equal to 0 degrees, and in this case the abscissa of points A and B is sigma x. So the abscissa of point A and B will be 0. So A will be vertically below B when theta is 0. right? This would be just coming in over here. So that is what shown is over here. A is vertically below B, and that's why they say that the abscissa of A and B is sigma x. Okay, so that's what, and abscissa of A was sigma x, but right now the abscissa of A and B both will be sigma x because of this special case. Similarly, the abscissa of points D and E will be sigma y. So D and E, okay. So E, remember the abscissa of E was sigma y dash. Now also it will be same, but D will come vertically below E because theta is equal to 0. So D and E will be sigma y dash. So the abscissa of this will be sigma y dash. The shear stress tau xy is represented by the downward ordinate of point A and by the upward ordinate of point E. Okay, so the shear stress tau xy is represented by the downward ordinate of point A over there, this one, and the upward ordinate of E. Okay, and just because you have to only trace the point A and E. Okay, so the ordinate of E was tau x dash y dash, and it still remains the same. Okay, and that's where you see this these terms. We have so we have also drawn the line ACE. ACE. This line has been drawn. Okay, labeling its endpoints x and y as indicated. So the endpoints of this line have been indicated by x and y. Okay, so that's the special case which we considered. And in the very last figure, all what you have done is for this special case, you in which x and y were the ends of line AE, this special case, what you have done is you have drawn a circle with C at the center. Has been constructed using the line xy as diameter. Also shown is the diameter x dash y dash corresponding to the orientation of the line ACE in figure 4.16. Okay, so this thing which we had has also been shown by a dashed line over here. Okay, it was for not theta equal to 0, and this one is for theta equal to 0. Okay, okay, so once you have this circle in front of you, and the angle between the xy diameter and the x dash y dash diameter is same. So xy diameter is already known, x dash y dash diameter is so this is the x dash y dash diameter. Okay, sorry, so in this circle you will have these two diameters x y and x dash y dash, and this is something which we will, so this circle is called the Mohrs circle. Okay, the construction of this you have already seen, and we will continue our discussion with this circle in the next class. Thank you.